Hello, and welcome to Functional Groups, Intermolecular Forces, and Kinetic Molecular Theory. We're going to start by reviewing the functional groups. We've already discussed this, but it doesn't hurt to talk about it again. And then we'll go into how functional groups can interact with each other and do a little segue into kinetic molecular theory. Okay, so this is a quote that I really like from a professor, John McMurray. The chemistry of every organic molecule, regardless of its size and complexity, is determined by the functional groups it contains. Well, what is a functional group? A functional group is an atom or group of atoms that imparts characteristic chemical properties and defines a given class of organic compounds. Basically, you can think of it as a chemical motif, either an atom or a collection of atoms bonded together in a particular way. Now, before we explore this, it's important to know one and a half other definitions. A heteroatom is any atom in an organic molecule that's not carbon or hydrogen. And then R. R is just basically a catch-all. It's any extension of an organic molecule. So it's a carbon, and then it could be one carbon, it could be 18 carbons, it could be a billion carbons. It just basically says that the molecule keeps going. And something to kind of emphasize why R is useful is a carboxylic acid is a carboxylic acid, regardless of if it's bonded to one carbon or 18 carbons, or I said a billion carbons. So anyway, you can also denote R using these primes just to kind of signify that things can be different. So like you can use R prime, R double prime, just to show that you can have different groups coming off. Anyway, so functional groups. Let's talk about them. Halides. And we're going to kind of go through this a little bit fast. Halides are, oh, there's that R, when you have a halogen coming off of your organic molecule. So here, X can be fluorine, chlorine, bromine, or iodine. For example, this is a chloride. It's got a chlorine coming off of our chain. Benzene, also known as an aromatic ring, is a six-carbon ring that looks like it has alternating double bonds and single bonds, but actually they're each 1.5 bonds because of resonance. It's actually an average bond order between them. An alcohol is when you have an OH coming off of your organic molecule. An ether is when your carbon chain is split with an oxygen in the middle of it. And then amines are when you have a single bonded nitrogen to a carbon. They can be primary, secondary, or tertiary. So a primary is attached to one carbon, a secondary is attached to two carbons, a tertiary is attached to three carbons. And these three carbons, they could each be one carbon. So they could each be a CH3, for example. And if they are, that makes this thing called trimethylamine. Not that you need to go into the nomenclature of this. But anyway, essentially the key characteristic here is that you have a nitrogen with a lone pair of electrons, and it's bonded to at least one carbon. Then we have a bunch of functional groups that are their motif involves a carbonyl. A carbonyl is a carbon-oxygen double bond, and it turns out that having that carbon-oxygen double bond actually really changes the reactivity of a given set of atoms bonded together, hence why it creates these different functional groups. Let's go through them. So there's a ketone, which is where you have a carbon chain that has just one carbonyl, a carbon-oxygen double bond coming off of it. This is one that I have a mnemonic for. So imagine you take this and then you imagine you take this ketone and you kind of color it in. What does it look like? It kind of looks like a keyhole. It's a ketone. Hey. It is easy to mix up the different carbonyl containing functional groups. So what a carbonyl is bonded to is important. In the case of a ketone, both this group and this group have to be a carbon. They can't be a hydrogen. They can't be an oxygen or a nitrogen. Because if one of them was an oxygen, you'd have an ester. So an ester is when you have that carbonyl motif right here. And then it's directly bonded to another oxygen. And that oxygen then is bonded to another carbon. So then it continues on. Okay. Esters are what's found in the material polyesters. Polyesters have multiple esters, hence the name. An amide, very similar, except you have a nitrogen instead. So instead of an oxygen, you have a nitrogen here, and you can have a continuation of hydrocarbon. You can actually have a hydrogen there as well. It doesn't matter. As long as you have a nitrogen adjacent to that carbon-oxygen double bond, you have yourself an amide functional group. These are really strong bonds. These are actually the bonds that make up um, the bonds that hold together the amino acids in proteins in living things. A carboxylic acid looks a lot like an ester with one important distinction. Instead of having a carbon coming off of it, it has a hydrogen. This is a terminal functional group. It can't continue on because a hydrogen can only take one bond. So a carboxylic acid has to be anchoring a molecule. You can't have a carboxylic acid and then more stuff after that. Whereas an ester, you can have like an ester functional group, like so. And then maybe you have one carbon or two carbons or three carbon. Like an ester is plopped in the middle of a molecule, whereas a carboxylic acid, once you get to this end of the line, and this R could be one carbon. In the case of acetic acid, it could be a bunch of carbons. Doesn't matter. As long as you have that collection of atoms, it is a carboxylic acid. Okay. Oh no, did the wrong thing. 1 second. Okay. And then an aldehyde is a carbonyl with a hydrogen coming off of it. And this is actually one that I have a mnemonic for. It's not a great mnemonic, but it's one that I like. If you draw a skeletal structure, you don't need to draw hydrogens attached to carbons. Let's call this hydrogen Al. Hi, Al. Oh, if we draw a skeletal structure, what happened to Al? Well, we don't have to draw Al, so you might say Al is hiding. Al did hide. Ha, get it? Because uh, anyway, just an application of this. So here are a few different carboxylic acids. Check this out. So this first one up here, when you have a long hydrocarbon chain, long hydrocarbon chains tend to interact with lipid bilayers, with lipids in general. And so sometimes long hydrocarbon chains will get this prefix fatty. So if you have a long hydrocarbon chain, this is fatty, and you have a carboxylic acid, that makes this a fatty acid. This one here has no double bond, so this is a saturated fatty acid. If you throw in a double bond, you get an unsaturated fatty acid. So here we have two different examples. And all of these have the same number of carbons. They all have 18 carbons. Two of them have double bonds. What's the difference between the two of them? Because it turns out actually one of them is a lot healthier to ingest than the other. The first one is a trans fat. It has hydrogens located on opposite sides of this double bond. Therefore, it is a trans conformer. The other one is a cis fat because the hydrogens are located on the same side. And cis fatty acids are actually what you find in all natural plant oils. Trans fats are what you find in partially hydrogenated oils. Saturated fatty acids are what you find in butter, for example. So this is actually stearic acid, which is the primary component of butter. Cool. All right. So now we're going to switch gears and talk a little bit about intermolecular forces. Um, what are intermolecular forces? Well, let's draw two distinctions. An intramolecular force is a force within a molecule. Intra means within. So, for example, intramurals are sports that are held within a given institution. Um, these are like covalent bonds, for example. Covalent bonds hold together a molecule. Intermolecular forces are forces between two or more different particles. Um, these are in general weaker because covalent bonds are super strong. If you were to throw a bunch of energy into two water molecules interacting, it's not going to break the oxygen-hydrogen bonds, rather it'll pull apart the waters. Regardless of if it's an inter or intramolecular force, breaking bonds or interactions requires energy. It has to absorb. So these are endothermic processes, whereas forming bonds or interactions releases energy and is an exothermic process. And just looking at these two water molecules, they're oriented this way on this slide for a particular reason. The oxygen has a partial negative. The hydrogen has a partial positive. Negative, positive. There's an attraction. Um, so these covalent bonds holding together the water, so these are two covalent bonds, these are two covalent bonds. These would be examples of intramolecular forces. And then this interaction between these two different waters is an intermolecular force. Okay, so that's intermolecular, whereas the intramolecular are the covalent bonds. Generally, again, intramolecular forces are stronger as they hold together the molecule, and then it's generally easier to pry apart two molecules than it is to blast apart a molecule into its atomic pieces. Okay, so let's talk about different types of intermolecular forces. First of all, London dispersion forces. Basically, anything that has electrons has London dispersion forces. And London dispersion forces arise from the fact that these electrons are just kind of cycling around the nucleus in a sort of random fashion. So they're randomly moving about their orbitals, and sometimes they're more on the same side of the atom than the other. This can create a temporary dipole. So not like a pure dipole where you have two different atoms of different electronegativity bonded together, but here what we have is these electrons are more on one side of the atom than the other, and that creates a partial negative on one side and a partial positive on the other. Turns out that can actually help hold together two different atoms, or two different molecules. So if you have two heliums and they're both doing that, notice that we have a partial negative here, a partial positive here. That will actually create an attractive interaction between the two. This is temporary, though, because if the electrons keep moving around, then you're going to lose the partial positive, partial negative. So it's not a permanent dipole, but it is there for a bit. It's a transient dipole. Um, those are London dispersion forces. Now, imagine if you have more electrons. So helium has 2 electrons, neon has 10 electrons. With more electrons, there's more of a capacity to have a larger partial negative and a larger partial positive. And we have our electron-rich side over here, and we have our electron-deficient side over here. The electron-rich side is going to be more partial negative, and the side without the electrons is going to have more of a positive charge because there's more protons in neon, and they're not really being shielded by these electrons. Anyway, it could interact with another neon, and this is more of a sizable interaction than you'd get from, say, helium. So this gives us a greater potential dipole. And this is kind of the general shtick behind London dispersion forces. The heavier your atom or molecule is, the more of a capacity for London dispersion forces they have. So the more tightly they're held together. Um, there's other types of temporary dipoles. So instantaneous dipoles form when there are more electrons on one side of the molecule or atom in the case of noble gases than the other. And since electrons are in constant motion, here's an example. Let's just say we have like H2. So there's an electron cloud kind of moving around. The electrons are being shared relatively evenly. But sometimes electrons will be more on one side than the other. And to help kind of denote this, we can use electrostatic potential maps, where red equals high electron density and blue equals low electron density. Anyway, it's just kind of a useful way of kind of plotting out electron clouds to show why molecules interact with each other in certain ways. Um, this is called a temporary dipole because it's based on the random movement of electrons. But this can induce another temporary dipole. So if you have, for example, two hydrogen H2 molecules next to each other, and one of them ends up having a partial negative on one side and positive on the other, that partial negative over here is going to scare away the electrons on this molecule to induce a partial positive on this side, and that's going to help hold these together. Now, not much. Hydrogen, being a very, very small molecule, doesn't have much in terms of intermolecular forces, but it's still something. So these are called instantaneous dipoles, and instantaneous dipoles can induce instantaneous dipoles in neighboring molecules. And we call these dipole-induced dipoles, because you have the temporary dipole inducing another dipole. Interactions between induced dipoles are known as London dispersion forces, and they depend on the polarizability of the molecule and the distance between these interactions. How can you increase these? Generally speaking, greater mass. More mass means more electrons, and more electrons means you can have a greater partial negative versus partial positive. The other way is more available contact space. So basically more surface area. If you think of Velcro, if you have two Velcro balls, you can attach them together, but they're easy to pull apart. If you have two Velcro strips, stick them together, it takes a lot more to pull them apart. It's very similar with London dispersion forces. Intermolecular forces have tangible impacts on physical properties. A good example of this is melting point and boiling point. Melting point is the temperature at which you have enough kinetic energy to turn a solid into a liquid, and boiling point is the temperature at which you have enough kinetic energy to turn a liquid into a gas. Let's do a little case study here, and let's look at propane versus octane. In these cases, which one would have more intermolecular force or more London dispersion forces? You said octane, you're correct. So octane is a much heavier molecule, ergo Latin. It has a greater electron cloud around it to allow for a greater temporary dipole. It also has more surface area. So if you look at propane, propane has a little bit of surface area where it can interact with another propane, but octane, being much more spread out, has the capacity to interact more significantly with another octane molecule. And when you think about things like melting point and boiling point and how surface area relates, you can think about Velcro. If you have a Velcro ball, for example, and you put it on a strip, pretty easy to pry off that Velcro ball. But if you have two Velcro strips with greater surface area and you put them together, it's going to take more energy to pull them apart. With that in mind, which of these two molecules do you think would take more energy in the form of heat to break apart the intermolecular forces? Well, propane, pretty easy. You supply a little bit of energy, you're able to pull apart two propanes. With octane, we're supplying energy, we're supplying energy, we're supplying energy, we're supplying energy, we're supplying energy. We're still supplying. Oh, there we go. Okay, we gave it enough. There it goes. Okay, so that's an example of like a boiling point here. In terms of actual data, propane boils at negative 42 degrees Celsius. Octane boils at 125.6 degrees Celsius. That's a significant difference, and it's all because of the mass and surface area, which is greater in octane. So London dispersion forces actually make a pretty big difference. And actually, these are two molecules that, if you think about what they are IRL under standard conditions, so propane is used as a gas to be a fuel. Octane is a liquid under normal room temperature, ambient temperature, and that's what we put into cars to make them go vroom. Okay, so before we continue, let's just do a little practice here with functional groups. Functional groups are super important, and this is an example of a functional group. This is called a beta-lactam group. We have this amide in a 4-atom ring. So all of these molecules contain a beta-lactam group. And what's kind of cool is this beta-lactam group actually tricks the cell wall creating machinery or proteins of gram-positive bacteria And rather than them creating links between each other, they create a link with these antibiotics, and then that puts little holes in the cell wall, and then they can pop. Thanks, beta lactam. There's actually like, a lot of cool chemistry that goes on beyond there. Anyway, functional groups are important. Let's see if we can identify some. So take a moment. Feel free to pause as you go through this. This is a chemotherapeutic drug, Taxol, and it's got a ton of functional groups. First of all, let's do this functional group. What is that? And in between each question, I'll give like 5 seconds. So if you want to pause, feel free to. What is that functional group? It's an amide. What's that functional group? It's an alcohol. And one thing I wanted to point out, just because this is oftentimes a point of confusion, it might look similar to a ketone, or excuse me, similar to a an ester. Excuse me, similar to a carboxylic acid. Um, a carboxylic acid has an OH group immediately adjacent to a carbonyl. So it has to be attached to that carbon-oxygen double bond. This one, you'll notice that carbonyl is 2 carbons away. Therefore, this is an alcohol. Just want to point this out because sometimes these subtleties, especially when you're first doing this, can be a little, can take some time to really get used to. Okay, let's continue. How about that functional group? You got it. It's an ester. What about that functional group? Yeah, that's an ether. How about that functional group? It's a ketone. All right. So speaking of functional groups and the motifs that these arrangements of atoms we have, different functional groups have different types of intermolecular forces. So here's another depiction of London dispersion forces and ion-induced dipoles. Generally speaking, large molecules with greater surface area are more polarizable and have greater London dispersion forces. Okay, so anyway, again, London dispersion forces are when you have random movements of electrons that can create a partial positive or negative charge on a side of the molecule. Now, if you introduce an ion into the mix, so this is an Na plus, that Na plus, because it's positive, is actually going to draw electron density toward it, giving us a partial negative on one side of the molecule and a partial positive on the other one. And this isn't a random assortment of electron density because here the electrons are actually flocking toward the positive charge. And it would be the opposite if you had a negative charge. If you had a Cl minus, for example, it would push the electrons to the other side of the molecule. This is called an ion-induced dipole because we have an ion that is inducing this temporary dipole. Now, if you move the sodium away, it would be gone and back to random movements. Okay? Again, this is called ion-induced dipole because we actually have a ion, in this case a cation, creating that dipole. All right, polarizability, not to be mistaken for polarity because they sound similar, means the ability to be affected by an electric field. Larger molecules have a greater electron cloud, which means they're more polarizable. If you're ever asked which of these molecules is the most polarizable, generally speaking, it is the heaviest of them. Now, once you move the charge away or take it out on an electric field, then they're going to go back to a random distribution of electrons. So again, this is a temporary dipole. Now, some more intermolecular forces to be explored. Dipole-dipole interactions and hydrogen bonding. If you look at butane versus propanol, they're very similar in terms of molar mass, but notice that their boiling points are about 100 degrees different from each other, 100 degrees Celsius. Significant. And it's all because of that OH group. The OH group has sort of a twofold, it gives kind of a twofold boon to the intermolecular forces. First of all, it creates dipole-dipole, the ability to create dipole-dipole interactions. Dipole-dipole interactions are attractive intermolecular forces that are created by partial positive and negative charges, i.e., when you have a polar molecule. Any polar molecule is going to be able to do dipole-dipole interactions with itself or with another molecule of the same kind. So we've got a partial negative on the oxygen and a partial positive on the hydrogen, and technically on the adjacent carbon as well, whereas butane has no dipole. Now, this particular molecule also has the ability to do hydrogen bonding. Hydrogen bonding is a special type of dipole-dipole interaction where you have an especially pronounced partial positive and partial negative on hydrogen and one of three other atoms. We'll get to that in a moment, but oxygen is one of them. Okay, so here we have one propanol. This is just a visualization of how this happens. And here we have another propanol. What will happen is the partial positive of the hydrogen will interact with the partial negative of the oxygen. And these are pretty small atoms, so they can get pretty close to each other too. Anyway, so this is an example of a dipole-dipole interaction, and in this case, a specific type of dipole-dipole interaction, which is a hydrogen bond. A hydrogen bond is just a very specific type of dipole-dipole interaction. So if you look at this trend here, you'll see that water, even though it is one of the lightest molecules on this table, has the highest boiling point. Water does not have a lot in terms of London dispersion forces, but what it lacks in that, it makes up for in hydrogen bonding. Okay, so what's going on here? Partial negative on the oxygen, partial positive on the hydrogen, and this allows for that hydrogen bond interaction. And hydrogen bonds are pretty significant. You can see, whoa, that's a really high boiling point. It should be noted that if you're ever given empirical data, like boiling points or melting points, you can compare them to figure out which molecules have more versus less intermolecular forces. In this case, H2O has the greatest. A little bit of terminology. We call the hydrogen that is interacting in a hydrogen bond the hydrogen bond donor. And then we call the oxygen or fluorine or nitrogen that has the lone pair the hydrogen bond acceptor. Okay, so hydrogen bonds continued. There are three types of bonds that can act as hydrogen bond donors. They are HF, HO, and HN. The hydrogen needs to be directly bonded to the fluorine, oxygen, or nitrogen for this to be in play. And the commonality here is that they are all small, very electronegative elements. So it allows both for a polar bond, but it also, because they're smaller, allows them to get closer to other HFs, HOs, or HNs. I like to think of it as hydrogen bonding is fun. Fluorine, oxygen, nitrogen. Anyway. So take a moment and see if you can identify the intermolecular forces available in each of these. So feel free to pause and see if you can identify what the intermolecular forces are in that first molecule, the second molecule, and the third molecule. Okay, let's go through them. The first one is difluoromethane, and it has London dispersion forces. Basically, any molecule will have that. It also has dipole-dipole interactions because you have a partial negative side where the fluorines are, and you have a partial positive side where the hydrogens are. The fluorine and the hydrogen are not directly bonded to each other, so there is no hydrogen bonding in this particular molecule. This next one, tetrafluoromethane, has London dispersion forces, and that's it. It's a perfectly symmetrical molecule. All the dipoles cancel out, so in this case, there's only LDFs. And then the final one, which would be methylamine, it has LDFs, classic. It has dipole-dipole interactions. And it also has that NH2 group, which allows for hydrogen bonding. Anything with hydrogen bonding is going to have dipole-dipole interactions as well. It's basically scaffolding. Everything has LDFs, and then, as long as it's a molecule, and then dipole-dipole interactions it can have, and then it can also have hydrogen bonding. But in order to have each one, in order to have hydrogen bonding, you need to have dipole-dipole interactions. Okay. And if we compare the boiling points of these, the first one is negative 52 degrees Celsius. The second one is negative 128 degrees Celsius. And that final one is 15 degrees Celsius, notably higher. It's because of that hydrogen bonding. Hydrogen bonding ensures the fidelity of DNA pairing and replication. Cool. So adenine and thymine make two hydrogen bonds, whereas guanine and cytosine make three, and that allows them to interact with each other when DNA replication occurs. Okay, so take a moment and see if you can rank these compounds from lowest to highest melting point. Again, feel free to pause. Okay, let's go through this. The one with the least is going to be 3 because it just has the 5 carbons, no dipole-dipole interactions, and we can see negative 130 degrees Celsius, pretty low. The one with the chlorine here, that adds dipole-dipole interactions, and that kicks up the intermolecular forces pretty significantly to give us negative 99 degrees Celsius. If we replace that Cl with an OH, now we have hydrogen bonding in play. Again, that increases the intermolecular forces. And then finally, NaCl is a salt. Salts, and things with ionic bonds tend to have much, 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 much higher melting points than any molecule that's just held together through covalent bonds because that electrostatic interaction of the positive charge and negative charge is significant. And this is a general approach you can take when you're comparing molecules that are of similar size and weight. Um, Look for which ones have dipole-dipole interactions and hydrogen bonding, etc. More IMFs, higher melting points, and higher boiling points. And again, salts have much, 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 much higher boiling points than molecules. These are just some summaries of intermolecular forces. London dispersion forces, basically any molecules with electrons have LDFs. Dipole-dipole interactions require a polar molecule. And then hydrogen bonding is an extreme dipole that we get when hydrogen's bonded to nitrogen, oxygen, or fluorine. Dipole-dipole interactions and London dispersion forces are collectively called van der Waals forces. There's a little terminology there. And then a more thorough summary of intermolecular forces. I don't necessarily recommend memorizing this. Just think about what's happening. Like each of these tells us. So ion-ion means you have two ions interacting, hence an ionic bond. Ion dipole is where you have an ion interacting with a dipole. So if you had like an OH group, that hydrogen has a partial positive charge. If it interacts with an ion, like Cl minus, that would be an ion dipole interaction. Ion-induced dipole is when you put a ion next to a molecule and it changes the electron density. Again, you don't need to memorize this. Just think about what each of these names is saying. And then in general, this is how you can assess intermolecular forces. For nonpolar molecules of the same molar mass but different shapes, the more spread out it is, generally speaking, the greater surface area and the more it can interact. So this would have more intermolecular forces than its counterpart over here. I like to think of it as the difference between meatballs and spaghetti. Which ones get more tangled? The meatballs are spaghetti. Spaghetti gets more tangled. The longer molecules can get more tangled. It's a little bit of a simplification, but they have more surface area to interact with. If you have covalent molecules that are of similar mass, then start to look for dipole-dipole interactions and hydrogen bonds. So if we compare these two molecules here, very similar mass, but the OH is going to kick this one to the next level. And then finally, if you have covalent molecules that differ substantially in molar mass, so here we have glycerol versus a cholesterol molecule here. If you have a really, really, really large molecule, the London dispersion forces are going to outweigh the dipole-dipole interactions. So oftentimes they're overlooked, London dispersion forces, but they can be significant, and especially in a large molecule. If you're ever given empirical data, just look at the numbers. Lower melting point, fewer intermolecular forces. Higher melting point, more intermolecular forces. One more time, let's compare these somewhat similar looking molecules. See if you can rank them from lowest boiling point to highest boiling point. Let's see how we did. Cumene is going to be the least, then acetophenone because it has dipole in it, and then benzoic acid, which brings into play hydrogen bonding, is going to be the greatest. Cool. Okay. And if you're curious, this is the breakdown of their melting points and boiling points. Again, very similar molecular weights, but very different intermolecular forces. Okay. And what if we look at these three molecules, tetrabromomethane, dichloromethane versus methane? And let's rank them from least to most polarizable. Remember, polarizable does not mean polar. Heavier molecules, more polarizable. So if we look at these, methane is the least polarizable, then dichloromethane, and then tetrabromomethane, because bromine is actually pretty significant. And if we compare these boiling points, again, this really emphasizes this molecule here, dichloromethane, has a partial negative and a partial positive side, which is all well and good, but its mass is so much less than the tetrabromomethane that it still has a lower melting point. So polarizability can actually make a really big difference in these. Okay. Okay, so one more time to practice a little bit. I'm going to pull up some molecules and then draw out the Lewis structure and see if you can predict what intermolecular force is. So after I pull up each name or each formula, I'll pause for 5 seconds so you can pause and yeah. Okay, so this first one here has LDFs and dipole-dipole interactions. How about this? Ammonia has dipole-dipole interactions, London dispersion forces, and hydrogen bonding because it's got NH. And then how about this? CBr4. Well, we actually already looked at this one. It only has LDFs because it's a nonpolar molecule, but it's still pretty significant melting point slash boiling point because it's a heavier, more polarizable molecule. All right, and then to finish up this video, we're going to switch gears and talk about gases. Gases, we're probably familiar with them, but what specifically are they? They're a collection of atoms or molecules, particles, that can assume the size of their container, the size and shape. So if you have a collection of gas, it'll diffuse out and fill up whatever space it's in. They exert a force called pressure, and that pressure comes from the gas particles bouncing off the walls. They have low densities, they're very spread out, and they are compressible. Like you can take gas and consolidate it into a canister. For gases, the kinetic energy of the environment is greater than the intermolecular forces. So what this does is because there's a lot of ambient kinetic energy, it allows these particles to be pulled apart and then they kind of bounce around. To understand kinetic molecular theory, um, let's let's look at elastic collisions using this incredibly realistic animation of a pool ball. In elastic collisions, all kinetic energy is conserved. So if we hit this cue ball toward these two balls, okay, the energy is conserved here, but it's transferred, and this would assume no friction. And let's see that again. The white ball loses kinetic energy, but it transfers it to the red ball and the yellow ball here. Um, the speed and directions can change, but the total kinetic energy remains consistent. And the idea of elastic collisions is going to be important when analyzing gases because as a simplification, we kind of say that in kinetic molecular theory that all the collisions that are experienced are elastic. So if you have one gas particle moving slowly and another one comes in quickly, it can transfer the energy. There are five key postulates of kinetic molecular theory. Molecules move in straight lines, and then they bounce around, and if they hit something, they can change their direction. It's basically random. Molecules are small. The volume of the molecules is much smaller than the volume of the container. In fact, kinetic molecular theory kind of postulates that that they're almost uh, a it's almost an infinitesimally small point in space are these gases. Molecules do not attract or repel each other, so this makes the assumption that there's no intermolecular forces, which isn't fully true, but it helps with simplifications. In a collision, rather than the molecules just bouncing off of each other, if you slow it down, they're going to interact ever so slightly before bouncing off of each other. Again, some of these aren't fully true assumptions, but they help to explain a lot. Molecules experience elastic collisions, and the mean or average kinetic energy is proportional to the temperature. Basically, you can think of temperature as a macroscopic manifestation of the kinetic energy in a system. More higher temperature means more kinetic energy. Yeah. Okay. Higher temp, higher kinetic energy. And we're going to finish by looking at these things called Maxwell-Boltzmann distributions. Maxwell-Boltzmann distributions basically plot out the distribution of different speeds of gases in a mixture. Because in a mixture, some gases are moving really slowly, some are moving really quickly. They don't all have the same speed. In fact, they have this broad distribution that kind of tails off here at the end. Um, okay, so first thing to know is that not all gases have the same speed, and therefore not all gases have the same energy. Um, for any given set of conditions, there is a vast array of um, speeds and therefore kinetic energies represented by these molecules. Okay. Now, temperature is a measure of the average kinetic energy of all of the molecules. Okay. So for a given temperature, there's always going to be the same average kinetic energy um, in the plot, but something that's moving at like 5 meters per second is going to have a lot less kinetic energy than something moving at 1,000 meters per second. Since gases have different speeds, it is useful to have a means of giving them a composite measurement of all of them. Enter root mean square speed, or URMS. Root mean square speed is the speed of a particle with the average kinetic energy of the entire sample. And to find, well, mathematically, it's defined as the square root of 3RT divided by m, where R is the gas constant, 8.314 joules per mole second. T is the temperature in Kelvin. Always important to use Kelvin for this and gas laws. And finally, m is the molar mass in kilograms per mole. This is the most overlooked thing, and so just make sure when you're using this equation, use kilograms. Okay, so don't use 16 grams per mole. Use 0.016 kilograms per mole for methane. The RMS speed can be found, can be estimated on a Boltzmann distribution by finding the topmost point and just moving slightly to the right of it. I'm just going to draw a little circle here. If you're estimating root mean square speed, you don't need to be super precise. Just know that you find the highest point, which is the mode, and you move slightly to the right of it. So in this case, it looks like it's about 500 meters per second, or about 490 meters per second. Close enough. Average kinetic energy for a system is 1/2 of the molar mass times the root mean square speed squared. And that's how root mean square speed is calculated for a given system. Okay, so that concludes our foray into kinetic molecular theory. We'll take a closer look at some Boltzmann distributions and temperatures and gas laws next week. So thank you for your time. Keep up the great work, and we'll catch you soon.